Hey everyone, welcome to homework 3.13. We're going to start with a test example problem. So this graph right here on the left, you don't even need to know what log is, but you can recognize that the places in which this graph intersect is going to be solutions that work for both graphs. So I'm giving you this problem because this is one I've seen where it's a little bit tricky. So we're looking at what is true about the solution set for the equation f of x equals g of x. And so when f of x equals g of x, we're looking for when these two graphs are intersecting. So the solution set is the value of the functions where their graphs intersect. This is a tempting response because we're looking at these values, but it doesn't specify exactly what value. So let's look at B. The solution set is the inputs that create identical y values or outputs. So this is going to be our best answer because the solutions are the x values that make these y values true for both equations. The solution set is the value of the functions where their graphs intersect the y-axis. No, those solutions for these two graphs have nothing to do with the y-axis. And so same thing for D here. It says, which of the following are solutions to the equation f of x equals g of x? So we're looking for the x values where this y value is the same. So it's between 4 and 5 here. So a good guess would be x equals 4.25. And then the second value is between 5 and 6. So another valuable guess there would be 5.75. All right, let's take a look at our lesson 13 practice problems. So here is a graph of P, an insect population that is growing. W weeks after it was first measured, the population grows exponentially. What is the weekly factor of growth for the insect population? What was the population was first measured, and write an equation relating P and W. So what we don't have here is we don't have the amount that it was in between 1 and 3. So in order to figure out what our factor is, we would need to have an idea of that, right? And so one way that we can look at that is we could pretend that this is the initial value. And so that would be, oh my goodness, 900 times the factor, which we don't know. Say we were to do to the power of 2 equals 8100. Right? And the reason is we would be pretending that this is 0th and this is then the second, right? And so then we're looking for what goes in here. So that can help us to narrow this down. So now we would have x squared equals 8100 divided by 900. So, oops, let me get that up here. So 8100 divided by 900 gives us 9. And so then we have equals 9. And then the square root of that would be 3. And so this means that the weekly factor is multiplied by 3. Now we can go ahead and we can test that out and make sure that that is in fact true. Let's check and see. If we were to do 900 times 3, we would get 2700. And then if we multiply 2700 times 3, we will in fact get 8100. So multiplying by 3 each time. What was the population when it was first measured? So since we're multiplying by 3 to go back down to the 0th term, we would divide by 3, and so we would get 300. It says write an equation relating P and W. So our population P of W equals 300. That's our first amount times the value of 3, the factor of 3, and to the power of our weeks. So here is the graph of the function f defined by f of x equals a times b to the power of x. Select all possible values of b. So all possible factors, okay? So we can't have a factor of 0 because then that would just be 0. So 1/10 would mean that we're decreasing by 1/10 each time. That is possible. Or sorry, decreasing to 1/10. I think that the slope would probably be a little steeper if we were doing 1/10, but it is possible. It's a decay function. C is also a decay function. D is also a decay function. E would not be decaying. It would be staying the same actually, because we'd be multiplying 1 a million times or however many times. 1/3 would be an increasing function, and 18 over 5 would also be an increasing function. So our best answers would be C, D, B, C, or D. I would imagine that C is the closest one. 1/10 would be that we are retaining very little, so that would be going down pretty quickly. 9/10 would be we're retaining quite a bit, right? And so it would be up above a little bit that. So these are all possible values, but C would be our most likely value. For number 3, the function f is given by f of x equals 50 times 1/2 to the power of x, and the function g is given by g of x equals 50 times 1/3 x. So both of these have the same starting value, but they have a different factor. 1/2 means that we're retaining more, we're retaining 50%, whereas 1/3 means we were only retaining about 33%. Kieran says since 3 is greater than 2, the graph of g lies above the graph of f, so that graph 1 is the graph of g and graph 2 is the graph of f. Do you agree? So she's saying that graph 1, which is this upper graph right here, she says graph 1 is g, which is 50 times 1/3 to the power of x, and that graph 2 is 50 times 1/2 to the power of x. Now this, again, she says that 3 is greater than 2. However, 1/3 is smaller than 1/2. So 1/3 being left each time means that this one is decaying faster. And so this represents actually graph 2. So no, because the factor shows how much remains, and 1/2 is greater than 1/3, so f of x is graph 1. All right, the function f is defined by, so again we have this similar situation here, graphs f and g. How does a compare to 50? So for g of x, if g of x is this blue line here, that means that a would be greater than 50 because the starting value for g is greater than the starting value for f. It says, how does b compare to 3? So here the function of g is starting higher, but over time it goes underneath f, which means f is growing faster. So that means that b would be less than 3 because this graph is not growing as fast as graph f. The dollar value of a car is a function of the years t since the car was purchased. The function is defined by this equation, which means that 3/4 of the value retains each year, or 75%, means we're losing 25% each year. How much was the car worth when it was purchased? So when it was purchased, it would have been to the 0th of times. So this would be $12,000. It's a pretty cheap car. What is f of 2, and what does this tell you about the car? So we're doing 12,000 times 3/4 to the power of 2, or squared, equals. And so let's go ahead and calculate that. I'm going to do 12,000 times 3/4. Oops, you could also write that as 0.75 if you like, to the power of 2 gives us 6750. And so that tells us 2 years after purchase, the car is worth $6,750. Sketch a graph of the function f. So we can just sketch a graph. We're starting at 12,000. You would want to label that. Oh, actually, I should label that higher because this is depreciating. So start up at the top, say 12,000, and it is decreasing. Okay, so you can just draw a sketch of what that would look like over time. If you'd like, you can, I need to stop trying to do that. You can put this in the calculator. Do 12,000, 0.75 to the power of x. Go ahead and graph that. Notice that we aren't going to be able to see this, so we can zoom out. Then we can see it a little bit better. We can also do our window and change this to 0. We're only going to look, let's say, at about 10 years, change this to 0, and then our x max, we know our maximum value was 12,000, so let's do 13,000. There you go. That's a much better. It looks pretty close to mine. Okay. About when was the car worth $6,000? Explain how you know. So we can go again into the calculator and go to second table. And we're looking for when the car was about $6,000. And so that would be between years 2 and 3. Oh, I'm not sure why that's happening. Sorry. Between years 2 and 3, because at year 2, it is $6,750, and year 3, let's see, it's $5,062. It is. All right. A ball was dropped from a height of 150, so that's our starting one. The rebound factor is 0.8, so 80% of the height. About how high in centimeters did the ball go after the third bounce? So 150 times 0.8 to the third power. Let's go ahead and calculate that. I just really need to stop. I don't know why I keep trying to do it. So 150 times 0.8 to the power of 3. Third bounce, right? Yes. Okay. So 76.8, so close to 77. A triathlon runs at an average rate of 8.2 miles per hour, swims at an average rate of 2.4 miles per hour, and bikes at an average rate of 16.1 miles per hour. At the end of one training session during which she did not run, she has swum and biked more than 20 miles in total. Is it possible that she swam and biked for the following amounts of time in that session? Show your reasoning. All right, so here we're looking at inequalities, and we want to see if this is possible for this person to have done. All right, so if she swam for 0.5 hours and biked for 1.25 hours, she goes 2.4 miles per hour. So when she's swimming, so 2.4 miles per hour swimming, 2.4 miles per hour times 0.5 for swimming, plus 1.25 hours biking, and she bikes at a rate of 16.1, and that has to be, it says she has swum and biked more than 20 miles total. Okay. So greater than 20 miles total has to be what that would be. So let's calculate and see what we get here. So, move this over here. We have 2.4 times 0.5 plus 1.25 times 16.1 is 21.325. So this is possible, yes, 21.235. That's a possible one. Swam for 1/3 hour, so she's going 2.4 miles per hour times 1/3 plus biked for 70 minutes, so 70 minutes, 70 out of 60 would give us hours, so 16.1 times, we'll do 70 over, over 60, over 80, over 60. Okay, will give us our time in hours. So let's see here, 2.4 times 1/3 plus 16.1 times 70 divided by 60. If you wanted to ahead of time put that into hours, you could. That's going to be 19.58. Which is less than 20, so that does not work. So this one does work, but this one does not. All right, write an inequality to represent the relationship between the time she swam and biked in hours and the total distance that she traveled. Be sure to specify what each variable represents. Okay, so she ran 20 miles in total, so we could say x, or greater than. So we could say x plus y is greater than 20. That's her total miles. And if she is running 2.4 miles per hour, and then so x is greater than 2.4 plus 16.1. So we can instead represent this as 2.4x plus 16.1. Y is greater than 20. The reason being that we are looking at actually only one inequality here. And as we showed up here, 2.4 times, that's the speed, times the actual time that she swam, plus 16.1 times the time that she biked will give us her distance. So we can also then graph this by plotting in what it would be at when x and y is 0 and finding our x and y intercepts, or we can put this into slope-intercept form. Either way is fine. For the purposes of this, let's go ahead and put this into slope-intercept form so that we have that practice. Again, that means that we are solving for y, so if 16.1 y is greater than negative 2.4, fix this, 2.4x plus 20, and then dividing by 16.1 on the whole thing. And so we will have y is greater than negative, and let's go ahead and do 2.4 divided by 16.1. Oh, nope. 2.4 divided by 16.1. Yikes. 0.1. And that 2.4 is negative, so negative 0.14. Negative 0.14x plus 20 divided by 16.1. It's 1.24. All right, so our starting point would be, if this is 1, 2, 3, 1.24 would be about here. And then that also means that when y is 0, x would be 1.24 divided by 0.14. So let's see, 1.24 divided by 0.14 is 8.87. So that would be about here. That's our endpoint. And it is going to be a dotted line because it is greater than, and we want to have greater than, so we're going to shade above the line. If we were to test a point 0, 0 is greater than 1.24 is not true. So this is the side we are not shading because that is not true. We want the side that does work, and so we would be shading that side there. All right, that is it for your homework. Your code word for today is butterfly. I don't really know why. It just was the first thing that came into my mind. So butterfly, put that at the top of your paper. If you have any questions, please feel free to reach out. Happy homeworking, and I shall see you tomorrow.